Ever feel like your query should be fast, but it's just not cooperating? You've got your where clause, your table's not that big, and yet it drags. This episode kicks off a three-part performance demo where I show how a good index can go bad. We'll look at execution plans, outdated statistics, and parameter sniffing. Each section will be fully hands-on using a Jupyter notebook inside Visual Studio Code. That just means I'm writing and running Python and SQL side by side inside VS Code, not in a browser. You can follow right along using the downloadable starter package I linked in the description. It's the same environment, same notebook, same commands. Don't worry if you're new to this format, I'll explain every line of code before we run it. Let's build a test table, query it without an index, then add one, and see why that one tweak can turn a slow query into a lightning fast one. We're working with a tiny database, just one table, 1,000 fake patients, and a column called diagnosis. Before we added an index, every time we searched for patients with, say, diabetes, SQL had to scan through every single row to find the matches. That's called a full table scan, and it's not the problem until it is. Now let's walk through the exact code we used to add that index and rerun the query. We're using SQLite with pandas to simulate a basic patient database. Let's break this down line by line. This brings in our tools. SQLite 3 lets us create a temporary database. Pandas help us display results like a spreadsheet and gives us tools for analysis. Con equals SQLite 3.connect. This line creates a new in-memory database. That means it's fast, temporary, and perfect for practice. It disappears when the notebook session ends. The cursor lets us run SQL commands. Think of it like your pen for writing queries. Without it, the database doesn't know what you want it to do. This next line of code, we're creating a table with 4 fields: ID, name, and diagnosis. Then we commit that change to lock it in. If we don't commit, it's like typing without saving. This next code inserts 1,000 fake patients by repeating 5 rows 200 times. We use execute many to run the same insert command multiple times with different values. It's like looping through a list of names and adding each one, then we commit again to save it. This print statement gives us a simple count to confirm that the rows were actually inserted. Fetch1 pulls the first value out of the query result. All right, here's our first real query. Select all patients with a diagnosis of diabetes. The read_SQL_query function runs the SQL and loads the result into a data frame. The head just shows the first 5 rows. Now we create an index on the diagnosis column. This acts like a shortcut or a lookup table that SQL can use instead of searching every row. This creates the index. We're giving it a name, IDX_diagnosis, so we can reference it later. And we're indexing the diagnosis column in our patient's table. What does that actually mean? It means SQL now keeps a sorted, behind-the-scenes list of all the values in that column, so it doesn't have to scan the entire table just to find the rows with diabetes. Think of it like putting tabs on your notebook pages. SQL can now flip straight to what it needs. All right, next line, con.commit. This saves the change. Whenever we create a table, add an index, or do anything structural, we need to call commit to lock it in. Then we reran the exact same query as before, but now with the index in place. This says select every row where diagnosis equals diabetes. The code itself hasn't changed at all, but the engine under the hood has. Instead of scanning every row like before, SQL can now seek directly to where diabetes lives in the index. Last line, this just shows us the top 5 results in our notebook, so we can confirm it's working without dumping the whole table. Now we can compare the timestamps of the query. So what did we actually prove here? Before we created the index, the query took about 0.1 seconds. After creating the index, it dropped to nearly 0. That might not seem like much here, but multiply that by hundreds of queries on a million row table, and you've got a real performance difference. The results look identical, but how SQL finds them is much faster under the hood. We just proved that indexes improve performance without changing the query. But sometimes even a perfect index fails. Let's look at why. Why? Because it relies on statistics, those little internal guesses about how much data lives in each column. Statistics help SQL estimate how much data it needs to deal with. If those stats are stale, SQL might pick a bad query plan even with an index. So now let's update some of the rows. Before we talk about statistics, let's look at what we just changed. In this command, we updated a large portion of the patient's table. Everyone over the age of 45 now has their diagnosis set to rare underscore condition instead of what they originally had, like diabetes or asthma. This kind of update simulates a real-world situation where data changes dramatically, like a batch update from a medical coding system or a reclassification event. But here's the catch. SQL doesn't automatically know how many rows were affected unless we tell it. That's where statistics come in. We're querying the updated data, but SQL may still be using an outdated query plan. Why? Because the internal statistics SQL relies on haven't been refreshed yet. Statistics are SQL's way of estimating how many rows match a condition. If you change a lot of data, like we just did, but don't update the stats, SQL keeps making decisions based on what it used to know. That means it might still expect only a few patients with rare condition, even though we just added hundreds. If it underestimates the row count, it might choose the wrong execution plan, like scanning instead of seeking. In SQLite, we don't get to see the execution plan directly. But in full-featured engines like SQL Server or Postgres, you'd use commands like update statistics or analyze to refresh those internal estimates. The lesson: if your data changes a lot, your query strategy needs to keep up, or your index could get ignored even when it should help. So what's the takeaway here? Adding an index isn't always enough. If SQL's still making decisions based on outdated statistics, your performance won't improve even if the index is technically there. The solution? Make sure your stats are refreshed regularly. In engines like SQL Server, that can mean running update statistics after big data loads or changes. In PostgreSQL, it's analyze. If you skip this, SQL keeps using the old map to navigate a brand new city. All right, so we've seen how indexing can help and how stale stats can quietly undo that help. But there's one more sneaky thing that can cause unexpected performance problems: parameter sniffing. Parameter sniffing is when SQL saves a query plan after seeing one set of input values, like diabetes, and assumes it can reuse that same plan for all future queries. That works fine when every value returns similar amounts of data. But here's where it can fail. If diabetes returns hundreds of rows, and rare condition only returns 5, reusing the same plan doesn't make sense. One should use an index seek, the other might work better with a scan or a different plan entirely. SQL tries to be efficient by saving time on planning, but it can backfire when the data behind your parameters varies a lot. This is super common in stored procedures or repeated app queries, where the first input value influences the plan for everything that follows. Let's demo it so you can see how the results are the same, but performance might not be. Even if your index is perfect and your stats are fresh, parameter sniffing can still mess things up. Let's run the same query with different parameters. We define a parameterized query so we can reuse the same statement with different values. This is common in production apps. This loop runs the same query 3 times with different values. In some engines like SQL Server, the first value might get sniffed and reused, which can lead to a bad plan for future values. Parameter sniffing happens mostly in stored procedures on prepared statements. You can fix it using option recompile, or you can fix it using option recompile or restructuring your queries. To recap, indexes are powerful, but they're not magic. Execution plans, outdated stats, and parameter sniffing all affect query performance. Today, we used a local SQLite demo, but these concepts apply to Postgres, SQL Server, MySQL, and more. If this helped, hit like, subscribe, and tell me what SQL topic you want next. I'll see you in the next one.